Okay, so welcome back to another video. So in today's video we have the following integral formula, and that's defined as the definite integral of f of x dx from a to b. We add this with our inverse function of the definite integral from our bounds of f of a to f of b, and then it gives out the following closed form that it's equal to b times f of b minus a times f of a. So it's a really neat like identity. And so what this whole video is we're just going to prove the left hand side is equal to the right hand side, and it's not as overcomplicated as you think. Today's video is really going to be short. We're just basically just going to do a bunch of substitutions. Well, not really a bunch, but there is substitution involved, but also integration by parts as well. And we'll see that everything will come out nice and smooth once we follow those steps. So to start this, I'm going to define. We'll start with our inverse function of the definite integral. So we'll start with our bounds from f of a to f of b of our inverse function f inverse of x dx. Okay, and if I let's say we perform a u-substitution, so I'll let x equals a function in terms of t, so we'll call that f of t. And if I differentiate both sides, we get that dx is equal to f prime of t dt. Okay. And so if I substitute everything back, so if I plug in our new bounds, so f of b, we just get that f of b is equal to f of t, so that means the new bound would be b. And then if I plug f of a onto here, and so the t over here for the lower bound would be a, and so I would plug f inverse of f of t, and then plug in our dx substitutions, f prime of t dt. Now, if you use your properties when it comes to inverse function, the inverse function of the function itself, you're just going to get the variable back. So this will just be equal to just t. So now we have that our new integral from a to b is just t, then multiplied by f prime of t dt. And now from here we can actually perform a not a u-substitution. We can perform a integration by parts. So of course we want to choose something that's easy to integrate and something easy to differentiate. So here I'm going to let u equals t, and so then dt is du is equal to dt, and then we're going to choose something that's easy to integrate. So f prime of t dt is equal to dv, then you integrate that, so we get that it's just f of t is equal to v. Okay. And now we can just plug in our pieces back. So we have u times v, and subtract with the integral of v du. Okay, so over here we'll have u times v, so that means t times f of t, right? And then subtract this with our integral. Of course, this is from, I should probably put down that this is integrated from a to b as well, just so. It's from a to b, and subtract this with the integral a to b of v times du, so this is just f of t dt. Okay, and if I plug the bounds over here, so we get that this is just b and then f of b, and then subtract that with a, then times f of a, and then subtract this with the integral of b to a f of t dt. And we're actually almost done. So far we've shown that the inverse function, so I'll actually put this down. I'll say that this is f of b and then f of a, and that's equal to our inverse function f of x dx. So the last step really is that we just got to add this back to the other side, and since this is f of t dt, simply we could just place that back for x, since t is a dummy variable in this sense. So that's pretty much it. So if I add both sides of the function with our definite integral over here, so we get that we get the following identity that we're being asked to prove. So therefore we have that substitute this back for x. It's just a dummy variable t, and then this is plus our the inverse, and then we have shown that that's equal to b f of b minus a times f of a, like so. And there we have it. So I told you it wasn't as complicated as you'd think it would be. All right, yep. that's a really good, well, really neat representation right there. So with inverse function, when dealing with integrals. So yeah, that's pretty cool if you ask me.